So cell potential under non-standard. Okay, we're not at SATP. We don't have 1 mole per liter. We don't have both sides. We've got whatever you happen to have. Once a voltaic cell starts to react, SATP is lost. Any thoughts of that first standard, and there was a lot mentioned, they're not all up there, that would be lost when you start running a cell or a battery? It's not the temperature, it's not the pressure, concentration. Once you start running a battery, you're not going to have 1.0 moles per liter anymore. You're going to start using it up. So as soon as you start running a battery, you don't get the voltage you'd predict in the table. Okay? The voltage will start to drop. This is not really a testable thing. It's just a connection to real life. If you look at voltage versus time, you start running a battery and the voltage stays steady at the first bit while you're at 1 mole per liter, then 0.95, 0.92. Okay? But eventually you start to see the voltage drop over time when you run the battery. And at some point the voltage will get so low, your phone says dead. It's not actually zero, it's just dropped below the threshold that your phone can work or that the light bulb lights up. Okay. If you have any significant deviations from SATP, you will not get the voltages in the table. If the concentration goes down, you think of, let's just say you had a battery made out of copper. Okay. I can't think of any battery, but we've been looking at copper. And you have 1 mole per liter of copper, and it starts reacting. The copper aqueous ion reacts and turns into copper. And maybe you go 1 mole per liter down to 0.5 moles per liter. To recharge it, you run this backwards, and we'll talk about this on Monday. You start taking copper and turning it back into the ion, and you drive that ion concentration back up. Okay. Now, this doesn't go back and forth spontaneously. If it spontaneously turns into copper, you've got to like plug a battery into the wall and put energy in to recharge it. So if you have a battery and that battery is at minus 20 degrees Celsius, you have an electric car and it's a cold Alberta winter, you're not going to get the same voltage out of that battery at minus 20 or minus 40. Or if it's really hot, batteries don't like being really hot, 60, 70, 80 degrees. Hey, electric cars have issues in Las Vegas in the summer because it's so hot. Okay? The same would be true if your drill or any battery. Okay? Everybody's probably had issues. You're outside and your cell phone maybe gets super cold. You have it in an outside pocket and it's minus 30 outside and your phone gets cold. It'll just shut off on you. When the battery gets cold, the voltage will drop. It won't work properly. You take that same phone inside and warm it up and your battery level might go back up. Okay? Just because you warmed that battery back up. Okay? Some other issues that cause deviations very specific to voltaic cells. If you had any coating on the electrodes, so if you picked your electrode up yesterday and you handled and fiddled with it, you covered it in oil from your fingers, that would cause an issue and you wouldn't get the voltage that you would expect. Okay. Okay. If you don't have a proper salt bridge, your cell won't run optimally. So if you had a teeny tiny salt bridge that was 1 millimeter in diameter and the ions couldn't move fast enough, or you had a huge air bubble, you're really sloppy making your salt bridge, you don't fill it all the way up, you flip it over and you got this huge bubble at the top that blocks the whole thing, or maybe it blocks 95% of the tube. Okay? You're not going to, you either read 0 voltage or a very tiny voltage if it's not totally blocked. Okay? Last, if your solution is made out of a whole bunch of ions, okay? So if a student messes up and doesn't pour our solutions back, it's half nickel, half copper, okay? You're not going to get the right numbers. And that's why we're very careful collecting those. Last bit, we're going to talk about more of the outside cells. We talked about voltaic cells in this slide and talk about, you know, having some issues with those cells. Okay? Now we're going to fully leave voltaic cells and talk about spontaneous reactions. And this course really focuses on corrosion, rusting. Rusting is a spontaneous electrolytic, a spontaneous redox process. So corrosion is when a metal reacts with anything in the environment that causes a spontaneous reaction and makes the ionic form, which you don't want. You want the frame of your Honda Civic to be solid iron. You don't want it to be iron 2+. That's weak, okay? And looks really ugly too. You don't want the door of your car to be iron oxide. You want it to be solid iron or solid metal. Now I'm going to focus this discussion not on any metal but on iron. What would cause this reaction? Iron to turn into iron 2+. Okay, is iron going to be an Ra or an OA? And then where do we need to go in the table to figure out what would spontaneously react with it? Okay. Neutral metals are always reducing agents. You could have looked it up in the table or remembered that pattern. So where is iron? Fairly low. It's in the negative 0.4 volt range. So iron is a reducing agent, and we want to have a discussion. What would work as an OA that's going to react spontaneously? We're going to look at the table, and then we have to think of, you know, what's actually practically going to be outside in the environment. So again, I'm circling iron on the table, and I'm going to box out all the oxidizing agents that's going to spontaneously react. Where do I want to go? Do I want to look down or up if I want a spontaneous reaction? Up above. So I've got to go above iron, and we're looking at all of these guys and thinking, what might you actually find outside? Okay. If you look at the top, you're not going to see any fluorine gas outside corroding your car. Okay. So let's get a few. We're not going to spend the time to get every possibility out, but let's get maybe 2, 3, 4 examples from students. So does anybody have a thought of a pairing or an individual OA that would corrode iron? Yep. Oxygen and water, is that somewhere here? What voltage is that at? So O2 and that's one reason we want to keep metals dry. When they're dry, they're much less likely to corrode. Any other thoughts? Oxygen and hydrogen. Yep, that's definitely there. Is that one there twice? Yeah, there's 2 oxygen and hydrogen. So you have oxygen and H+. Okay. Definitely going to corrode metals. Now, the more concentrated the reactants are, the faster the corrosion. So this will definitely corrode it. If you have a very acidic solution with a lot of H+, you can see a lot of corrosion quite quickly. Let's maybe get at least one more. The last one I'll highlight is H+ by itself is above iron. Okay. So all you need is acid. Okay. Even if you don't have the oxygen, it's going to be corrosive. Okay. So these are all things you cannot get near an iron-based automobile or an iron-based anything outside because it will corrode. So we're going to end with a slide and a picture. How are we going to prevent this? What do people do, engineers do, to prevent water from touching their car? Okay? Because clearly you can't stop it from raining. Your car's going to get wet. That's a guarantee, unless you only drive it in nice sunny summer days. So this is a pretty big list. There's lots of techniques that are done. Okay. The first thing you do to prevent corrosion is you have an oxidizing agent and you put a barrier. Okay? That double line is meant to be a barrier like a paint. If the OA and the RA can't touch each other, they can't transfer electrons and your car is fine. Okay? So you might think the paint is on the car to make it look good. You're horribly mistaken. We do not paint cars to make them look good. Okay? They might make you pay extra money, but the paint is there to prevent corrosion. Okay? That's the #1 purpose. Okay? Sometimes I'd even put a plastic layer on front of my paint on the nose of my car to prevent rock chips from chipping the paint, and then water and oxygen get at the paint, get at the metal in my hood and corrodes it. Okay? So we paint things, #1. Second, there's other preventive coatings that we use other than paints. And I want to talk about galvanizing nails. Okay? We coat things in zinc sometimes. Okay? When zinc rusts, it rusts rock hard. It makes a coating. You can go to Home Depot and buy an iron nail. Do not build anything outside of iron nails. If you build your deck out of iron nails, in probably 8 to 10 years, your deck will fall apart. Okay? But it could potentially kill someone if it's up high enough. Those nails will corrode, they'll shear right off. Okay? You're either going to use stainless steel, or if you've ever heard of galvanized nails at Home Depot, they've covered those nails in zinc. They've put a coating. Okay, that black is zinc. The zinc prevents water, acid, any of those OAs that we discussed from getting at the iron nail, and it keeps the iron structurally sound and keeps it strong. Okay? If you build a bathroom inside a house, you typically use galvanized nails because you could get moisture and water going into your wall. Certainly outside, you'd use galvanized nails as a coating. So that kind of ends the coating section. You paint it, and I'm just talking about galvanizing as an example. Zinc coating something. Okay. Another example. Okay. We're really going to use some chemistry with this one. Cathodic protection. Protect the cathode. Or use a cathode. Okay. This involves connecting a battery to the metal. Connect battery to metal, and you better do it the right way. Okay? You need the negative terminal to the metal. You're going to force electrons to the metal. You're trying to force the metal to be a cathode. When you connect the negative terminal of a battery to the metal, you are not letting the reaction spit out of electrons. You're forcing electrons at the metal. You're trying to make the metal gain electrons, which it won't do. Okay? But the key is you prevent the black forward arrow by forcing electrons at it. Again, the electrons can't leave, the reaction can't occur, and your metal just stays at a metal. Okay? This is often done to tanks underground. Okay? A lot of fuel companies, think Esso, Petro-Canada, if they want to protect a tank in the ground, they can connect a DC current to that metal tank, force electrons at it, and use cathodic protection to make that metal a cathode and protect it. Okay? The water is going to have moisture in it. Okay? The ground is easily going to be acidic. They're not going to prevent the OAs. Okay? They may not be able to protect that tank coating from getting scratched. Okay? But if they force electrons at it, they'll keep that tank from rusting. And that's cathodic protection. Okay? You better be a good engineer or technician. If you're a bad one and you flip the battery the wrong way and you put the positive terminal to the metal, you'll drive the reaction forward in a hurry. You destroy the whole tank the first night and be fired the next day and probably sued for the damage you did. You can add another metal that will become the strongest reducing agent. So find something that's going to react instead of the iron, a better RA than the iron. Okay? You'll sacrifice that other metal and protect your iron. So what's hidden is a bunch of metals that are better RAs than iron. So I'll let you write, and when you're done writing, start looking below iron and seeing what's there that you could add in. You need to find metals. We got zinc is below. If I have zinc attached to a tank, the zinc's the strongest RA, not the iron. The zinc reacts, the iron's fine. So I got zinc, chromium, aluminum, magnesium, sodium, calcium, barium, potassium, and lithium are all metals that are better RAs than iron, that will react instead of the iron. Now, any of those metals would work in theory. The one that works the best ends up being zinc. You want it to react, but not too fast, because you don't want to have to replace the zinc every day, and zinc's pretty cheap. So zinc is sort of the nice engineering compromise or trade-off. It works for the chemistry, cheap, not too fast, not too slow. Okay? So every ocean-going metal boat will have hundreds of pounds of zinc attached to the hull. All of these white specks are zinc. They're all sacrificial anodes. Instead of the copper water pipes or the iron hull corroding, the strongest reducing agent is going to react first. The strongest reducing agent is zinc, not iron, not copper. Okay? The zinc on the hull, is going to protect any metal above it. Okay? Once all the zinc is gone, boom, it's going to start attacking the iron. So you've got to replace the zinc yearly. Okay? But that's what that last example of a sacrificial anode looks like. You don't have to cover the whole boat. Okay? It's just the OA is going to get at the iron, and you electrically connect the zinc and the iron together. Okay? Zinc loses electrons more easily, so zinc loses them instead of the iron. Okay? Now, you would probably think, okay, if both of these metals spontaneously react with H+, wouldn't both react? And the answer is they both don't react. Only the best RA reacts. Okay? And that's why it protects it. It's not everything below H+, it's just zinc. Okay? So that's the sacrificial anode.